So the next topic in this series of lectures is about the initial volume problem in electron microscopy. So for these slides, I have chosen a presentation I did like 7-8 years ago, and still the ideas are still the same, but the conclusions are now quite different. Okay, so let's say that we want to have a 3D reconstruction, and we want to go from the projections of our images from the micrographs to a 3D reconstruction of them. So in the process, we will need something that is an initial guess of how the particle you are reconstructing looks like. That is the initial volume problem. So at the time, I would say there were three major bottlenecks. So the first one was the initial volume. So a few years ago it was a real problem. Now it is much less so, because there have been many algorithms trying to tackle it, and in a way some of the algorithms have. So there are so many, you run all of them and at least one of them will succeed. And so that is why I would say that now it is not so much of a problem. Then you have the 3D heterogeneity. This is still an open problem, I would say. So if your sample is heterogeneous, then reconstructing an heterogeneous sample is actually, at the moment, I would say, one of the factors that limit most the 3D the resolution that we achieve. The other one is high resolution modeling, and again, this high resolution modeling has advanced quite a lot. Okay, so why do we need an initial volume? Because the most common approach to 3D reconstruction goes in the following way. So you started with an initial volume, and then you have your particles. Here we are representing class averages, but they could be particles. And then you need to assign points of view to these individual particles. And for doing that, what you do is you project your initial volume in many directions, and then you compare those projections with the experimental ones, and then you decide for every experimental image which one is the reprojection that looks more similar. And then you take the direction from this projection direction, from this reprojection, so this line here, you get how you generated that image, and then you invert the process so that now you take all the experimental images with their associated alignment parameters and make a new 3D volume by just applying a 3D reconstruction algorithm, and then you have a new model that, and you iterate this process once and again. So now you generate new projections, then you assign the angles, you reconstruct, generate new projections, assign the angles, reconstruct. But if you think of that process, that is a greedy algorithm. So given the current solution, what we look for is the best solution in the vicinity of this model. So if you think of it as an optimization problem, so your initial volume, this initial volume would be just a point in the landscape of the goal function. The goal function is the similarity between the reprojections of your initial volume and the current and the experimental projections, the similarity or the error, the difference between those. So, and then you move into the direction of assigning the best angles. So the best angles is actually moving along the direction of highest slope. Maybe this is not too mathematically accurate, so yes, you cannot prove that this is the gradient descent, but it goes into that direction, or at least in a very slopy direction, so in a direction where the slope is high. Okay, so in optimization, you may be familiar with these plots where what we are doing is these are the contour levels of the landscape of solutions. So this is the goal function that you are trying to minimize, and then you start with an initial guess, and then you move into a direction that reduces the goal function, and it may be the one with the highest reduction, that is gradient descent, or it can be one that reduces quite a lot the goal function, even if it is not the maximum. And then you have a new initial volume or a new estimate of what the volume looks like, and then you update it again and update it again, and so on. So this is the typical procedure, and this is pretty greedy. So given the current solution, I'm trying to look a very good direction from the current solution. And the problem is that rather than these very smooth functions, we are trying to minimize a function that has a lot of local minima. And instead of being in 2 dimensions like this one, where we only have to choose 2 parameters, we are in a we have to choose many parameters. So let's say that we have 100,000 projections of this size, 200 cube, and then the volume is a parameter. So is what we are trying to reconstruct. So we have to minimize the similarity or minimize the error between the reprojection of the volume according to some point of view, some alignment parameters with respect to an experimental image, and then we have to find the volume and the set of angular assignments such that the overall error between our reprojections and the experimental images is minimized. And if you count the number of parameters that you have to find, the volume, because the images are 200 squared, the volume is 200 cube. So that gives almost 8 million parameters. And the remaining parameters are the ones of the angular assignment. So the angular assignment, if you have 100,000 projections, for every image you have to find the projection direction. Those are 3 angles typically. You can encode them with quaternions or whatever, but at the end you will have to find 3 numbers. And then 2 shifts, because the experimental images can be shifted in plane. So the reason is that the coordinate that you have chosen from the micrograph may not be exactly at the middle of the macromolecule. So you have to find 5 parameters per image, and that gives you 500,000 parameters. So at the end we have 8 million and a half parameters, and to be fair, these 8 million parameters, they are almost coming for free once you have chosen this 500,000. So the 3 reconstruction algorithms, they are pretty good, and once you fix the angular parameters, the 3 reconstruction typically is really good. So we have to find these 500,000 parameters, but still those are a lot of parameters. And there is a well-known effect that when you are minimizing in a very high dimensional space, like this 500,000 dimensional space, then these kind of goal functions, they have trillions of local minima. And some of the local, so you have many local minima, and even some of the good local minima, they can be very narrow. So either you are pretty close to the region where you can find the minimum, or you are totally lost and you will never find the true minimum, the true global minimum. And we are all familiar with this effect of Einstein from noise. This example was very nicely illustrated in this paper, And what they showed is that if you take 1000 noise images and you align them to a reference, then when you average using those alignment parameters, what you recover is the reference, despite the fact that the reference was never present in the original images. But the fact that you align some images with respect to something makes that something tends to appear in the 3D in the reconstruction. And you may remember from one of our previous lectures that we said that 3D reconstruction at the end is a kind of averaging. This can be simplified to an averaging. So this fact of aligning to a reference, actually this is in the field it is known as model bias, but mathematically it is just a manifestation of this local minimum. Okay, so how to choose the initial volume? So there are many choices. So the first one, and this is one of the most common, is to use a filtered volume. So if I'm reconstructing ribosomes with different ligands, different factors attached or not, I could start with a ribosome of the kind that I'm interested in, and then filter it to low pass filter it to, let's say, 60 angstroms resolution, and then start the reconstruction from there. So when I low pass filter it to very low resolution, like 60 angstroms, what I'm keeping is just the overall shape. So we are losing absolutely all details, but the size is the correct one. The overall shape is more or less the correct one, and typically this is enough to drive to be able to lead the optimization process. So that would be giving a relatively good initial point for the minimization. Okay, so this is one of the most common choices if you have something previously known that it can be safely used. Some other brave people, they design phantoms by themselves. So you could design a set of ellipsoids and spheres and then arrange them in space and use these as the initial point. So this is driving very much the process, but again, this depends on whether you are confident that you are able to construct such an object. So at present, no one is doing this. On the other extreme, you could think that if I initialize the process with just random noise, or with a sphere or an ellipsoid that has more or less the right shape, the optimization algorithm will be clever enough to go from this initial point to the global minimum. But these optimization algorithms, they are very much normally they are too greedy. So sometimes they can go away from the initial point, but some other times they cannot escape from here and they cannot never find the global minimum. So these strategies sometimes they work, sometimes they don't. If you don't have any clue about how the macromolecule looks like, you may try to use this random conical tilt. That is an experimental technique that takes a pair of images, so one at 0 degrees, another one at 40, 50 degrees, and then from the fact that you know that these two images are related by 50 degrees in tilt, you are able to reconstruct an initial volume with some problems, like having a missing cone, and this missing cone causes elongations along the direction of the missing cone, but you have something to start with. Here you have a representation of the missing cone. So we already know that projections are central slices in the 3D Fourier space, and if you think how the images in a random conical tilt experiment are collected, so you have some projections here, and these projections are tilted 50 degrees. So the 50 degrees tilted images are here, and they fill the space in a particular pattern, following a particular pattern. And this particular pattern has a missing wedge, a missing cone. So this missing cone causes that the volume that you reconstruct is elongated along the direction of the missing cone, so along this direction. Okay, so in practice that was not always working, and when we revised the math, what we discovered was that some very subtle details were not explicitly considered in the theory, and when specifically the shifts, and so the fact that the particles were not picked exactly at the middle. And then we extended that theory to include the shift, to include arbitrary orientations of the tilt axis, and also to be able to align not just the two tilted and untilted images, but the tilted images with respect to a class average. And with all those modifications that are explained in the next video, then we were able to make very nice random conical tilt reconstructions with very few projections. Okay, the final way, and it is the way that it is currently done, is by computational means. So try to devise algorithms that are able to produce from the set of images a suitable initial volume. And if we look at our optimization problem again, we realized that there were several problems. The first one was that there were many local minima that we were minimizing in a very high dimensional space. And the last one was that that we had many that we were greedy. Okay, so the first thing we can do is to remove the dimension, to try to solve the dimensionality problem. And the second one is to try to work in a less greedy way. And the final thing that we can try is to try to optimize a goal function that has fewer local minima. And for reducing the dimensionality, so instead of working with 100,000 projections, we can work with the classes, for instance, with the 2D classes. So these 2D classes, you can have, let's say, 100 2D classes. So you only have to find, instead of 500,000 parameters, now you have to find 500 parameters. So that would be a very strong simplification. The other one is to try to work with a goal function that has much less minima, many fewer minima. And for that, what you can do is to increase the signal to noise ratio, and again, working with classes helps into that. Or work with common lines, which are supposed to have a better signal to noise ratio. The other one is the optimization algorithm, and I would say this one is the trend that now has found more success. So don't be greedy, and we will see different ways of not being greedy. So this is just a reminder of the central slice theorem. So the central slice theorem said that if you had a 3D object and you had a projection of that 3D object, then the 2D Fourier transform of the projection is one of the planes of the 3D Fourier transform of the 3D object. And this plane has to go through the origin, so it is one of the central planes, and the coefficients are exactly the same up to some scaling factor. Okay, so if a projection, so we have, let's say that we have two projections. So if we have two projections and we have the 2D Fourier transforms of the two projections, so this is the Fourier transform of this one, this is the Fourier transform of this one, then we must find we know that this 2D Fourier transform is one of the planes in the 3D Fourier space this one is also a plane in the 3D Fourier space. So both planes intersect at a line. So there must be a line of Fourier coefficients in the 2D Fourier transform and in this 2D Fourier transform that they're exactly the same. So the problem now boils down to identifying which are the lines that are shared by 2D Fourier transforms. And instead of working with a 2D Fourier transform, we can transform the problem into a real problem, which is easier to work instead of complex numbers. And it can be proved that finding these common lines in the 2D Fourier space is equivalent to finding common lines in the sinogram space. So the sinogram is a concept of projecting a 2D function into a 1D line. So for doing that, what we will do is to integrate our image. So let's say that we have this image and we want to integrate that image along a particular direction. So you take all the lines that go through your image and then you compute the integral of the image. So this is the image, this is the integral of the image along these paths. And then you have a parameter that is what is the shift with respect to the origin. So the origin is here. Here you have how much the line is shifted with respect to the origin. And then you have a 1D profile. And you can repeat this process. So this would be our first projection. So you can, so this axis T will be how far you are from the origin. And this is the 1D projection. Okay, but now we can turn our image and project it again. So if we call the rotation angle theta, the projection we just obtained is the projection when theta is equal to 0. So now I take this profile and put it for theta equals 0, and then we have the axis T. But then I can project at 45 degrees, and then I have the projection for 45 degrees, and then I have the same axis T, that is the how much this point is shifted with respect to the origin. And I can make the projection at 90 degrees, and in general I can do it at any possible angle, and I have transformed my 2D information, my 2D image into a 2D function, but now the axes of these 2D functions are different. So this is x and y, this is theta and t. Theta is the angle at which I have projected, and t is the distance to the origin of the 2D object. So this new construction is called the sinogram. And it can be proved that identifying the common line between two images. So let's say I'm interested in the common line between this image and this image. So it can be proved that that problem can be solved through the sinogram. So I can transform this object into its sinogram, this object into its sinogram, and then take vertical lines and then compute what is the correlation between these vertical lines. So I can take, for instance, this line here, this line here, and then compute the correlation. The one that maximally correlates is the one is related to the common line in the 2D Fourier space. Okay, so we have been talking about the common lines between two projections, but this alignment is ambiguous because there is still a degree of freedom that we have not fixed. That is, so I have found that these two projections share this line, but still I don't know what is the relative position of this plane along this axis. So I can rotate it along this direction, and all of these possible rotations, they still have the same common line. So now if I add a third projection if I add a third projection and compute the common line between all pairs, I will have 3 constraints, and from these 3 constraints I will be able to construct, to place to find the relative orientation of the 3 projections and then place them in a unique way in the 3D Fourier space, unique up to an overall global rotation. But the problem with this is that we are working with very noisy images, and very often we find the wrong relative orientation between the 3, and then by adding more and more images to the process, we cannot find anymore the relative orientation, because we are already set in an incorrect coordinate system or coordinate. So this defines the relative orientation between the 3, and trying to add the new ones makes the process inconsistent. So it was proposed a solution to that was, instead of working first with 3 and then adding the rest, why not to try to find the overall solution to the whole problem. So if you have n images, then make all the possible comparisons. And the way it was proposed at that time, it was again a greedy optimization, so leaving n-1 images fixed and optimize one image, and then you move to the next image and you try to find the correct orientation. But the problem with this is still the greedy optimization. So if you start from a wrong position, then very often you cannot converge to the right solution. So in practice, this was a nice idea again, but it is not so much used in practice. And then there have been a number of works dealing with this 2D projection, with this common lines in Fourier space, and there have been very nice algorithms, especially those with from the group of Amit Singer and Joel Skolniski. But again, in practice, they are not so much used. And there have been, these are kind of the same algorithms. Okay, so there has been more proposals. So one of them, for instance, was trying to compare all possible pairs of images or classes, and then trying to construct a local transition probability matrix, and it was done with images. And then from this local transition probability matrix, somehow try to infer the Euler angles. And although the idea seems to be very appealing, in practice the number of images is really limiting the applicability of this approach. And then we have another family that are the stochastic optimization algorithm, and I would say this one is the one that have at present the highest success rate. So the idea is that do not try to be greedy. So try to allow for errors from time to time, and this is well known in the optimization procedures like stochastic optimization. So for instance, if you start here, a deterministic optimization algorithm would go just to this local minimum, and if you start here, it would go to there. But the stochastic optimizations, they allow for errors. So once you are here, you are allowed to go up against the goal function. So now the goal function is worse than it used to be, than the best one that you have already found. But by allowing these errors, you are allowed to explore other local minima. And there are many algorithms like simulated annealing, stochastic hill climbing, SPSA, swarm algorithms. So there are really many that they have even global convergence theorems. As always, if you run the algorithm forever and under certain conditions, so forever means infinite numbers of iterations. So in practice, sometimes they get also trapped into local minima. But they have been very successful, and I would say this is currently the trend. One of the first algorithms proposing that was this one of Ogura and Sato. And the idea was very simple. So you start with, let's say, 200 images, and then you assign randomly the 3D alignment of each one of them, and then you take one single image. And in this single image, you assign a new set of angles. If that set of angles improves the reprojection error, you keep it. If it doesn't improve, then you still may keep it, but with a given probability. And this given probability depends on something that is, so as iteration goes, they allow for fewer and fewer errors. So this algorithm is called simulated annealing, and they showed that they could, for instance, go from something that is completely random to the right structure in many cycles, 700 cycles. This probability that tells you whether to keep a worse position or not is related to something called the temperature. And the temperature at the beginning it is very high. That is why the algorithm is called simulated annealing, because it tries to simulate the way that a metal or a crystal anneals with the temperature. So at the beginning it is very hot, so you allow a lot of movement, but as the iterations progress, then you allow for less and less movements, incorrect movements. Okay, so at present, this is not the algorithm of choice, but they follow more or less this stochastic optimization flavor, even if it is not exactly the same procedure that we have explained. So, for instance, there have been a number of works by Hans Edmund on the stochastic optimization using common lines and using simulated annealing with differential evolution. So, well, there are different several works on this. So mixing common lines with stochastic optimization. There was also another proposal to work with the full data set rather than the classes, for instance. And well, the problem with this algorithm, so it goes more or less again along these lines of stochastic optimization, but the problem with this proposal was that it was taking too long. And then I would say this is one of the most successful approaches, this stochastic gradient descent. So stochastic gradient descent is a technique that is coming from other computational domains, especially from the deep learning algorithms. And the idea there is that we don't need to work with the full set of images at the same time. So if you have all these images, you may just take a random subset of these images and then run a gradient descent, but only on these 5 images. And for the next iteration, you take a different random subset of projections, and then you run a gradient descent with just those images. A gradient descent, just one iteration, and by doing this, you are somehow allowed to explore different areas of your goal function, and you are allowed to so the goal function actually is changing from one iteration to the next. So the landscape of solutions is different when for subset 1 than for subset 2, and that is why it is so successful, because at the end, overall, all these different landscapes, they share a common shape, more or less, but with just a lot of noise around that shape. But since you are changing the landscape, the goal function continuously, so at every iteration you have a new continuous function, the gradient descent cannot get trapped into local minimum, because the local minimum of the current iteration is not the local minimum of the next. And they have been very, very successful in that, and that was the idea behind CryoSpark. There have been other variations on this. So, for instance, this deterministic annealing with some Bayesian prior, and you have the details in this paper, for instance. And RANSAC is another proposal in which the algorithm assumes that in this process of finding a volume that is compatible with the projections, at first, when you are assigning the angles at random, there will be many mistakes. So in a way, you can think of it as in this figure. So in this figure, the line would be the volume and the points would be the different projections. So you assign randomly the angles to all projections, but some of the angular assignment, the random angular assignment, they will be consistent with each other just because of chance. Especially that is true if you use relatively few projections, and then if you reconstruct using those images that are more or less consistent to each other, the rest will not be consistent because they were randomly assigned. But if you identify how many are more or less consistent to each other, and you make a 3D reconstruction out of those, the 3D reconstruction would be the model. The model here in this plot is the line. Then you might find volumes that are slightly better than the rest, and then you let those volumes to drive the process. And it is successful in many situations. In some others, they are not. This is not successful, but yeah. So the point is to try many different algorithms. None of them is 100% foolproof. So there is no algorithm that can absolutely claim that they always find the right structure straight away from the beginning. And this was another idea, this Reconstruct Significant, and we showed in that paper again that we can start from a random assignment to the final, to the correct structure over iterations. And the point here was a little bit different. So we had a couple of ideas. One was that, okay, so you have projection images or classes. Typically this is run with classes at the beginning, and you have the projection directions from the current case. And then for every image, so let's concentrate in a particular image. So for that image, we compare that image to all projection directions, and let's say that this is the maximum, but we know which is the maximum, which is the second best, the third best, and so on. So you can make a reconstruction with all the projections, or with the top, let's say with the 5% most significant projection directions, and that would be one of the ingredients. The other ingredient is that this projection direction has seen all the experimental images compared to it, so it can also vote. So that was a significant change in the way of thinking. So first, typically an image decides where to go, but the projection direction doesn't have anything to say. But in this algorithm, the projection direction is also allowed to speak, and then he may say, okay, you want to go with me, but I have seen many other images compared to me, and you are one of the worst, so I don't want you to go with me. So this is also put in a weight. So beside the weight of being significant along the green line, you also need to be significant along the yellow line. And then you have also EMAN. For instance, EMAN is we don't know. I don't know personally what EMAN is doing. They don't normally publish their method so often, but it is also somehow kind of random angular assignment. You have more options here, like this pseudoatoms approach. That it is also nice. This is not so much used, but actually I don't see a fundamental problem with it. And here is a very interesting idea. So we were saying there are so many algorithms that you try your first initial volume with all of them, and then at the end you will have a whole list of candidates. And the traditional approach was that the user had to decide which one was a good 3D construction to start with. But that could cause a lot of bias, especially if the user doesn't know exactly the details of his protein. So this swarm consensus somehow takes all these like candidates, and then it borrows ideas from stochastic gradient descent, but they're not exactly the same. So it borrows ideas from there, from something else that is called momentum optimization. And the thing is that if you think of these as individuals in a swarm, then you let the swarm evolve and they share information between each other. There is a very nice video here where we can see this swarm optimization. So let's say that we want to minimize this function. So this function has only two parameters to minimize, and there are two local minima. One is deeper than the other. Okay, so then we will start with a random swarm. So we have many different possible solutions. Each one is a candidate. So in our setup of CryoEM, each one of these points would be a volume. And here are I said it wrong. So we don't want to minimize, we want to maximize. So we have three local minima. So we have these two and this one. That is the global one. Okay, so then so here are the three local maxima, and then they are following somehow locally this gradient. So this is a local gradient optimization, a standard one. So in our domain it would be just assigning angles according to the current solution, and then reconstructing the volume again. And as you can see, some of the minima, they have been more successful. So this minimum was not, this maximum was not very successful, and most of the particles are getting to here, but some of them, they got trapped into this local maximum. And then eventually, because in the swarm there is a crosstalk of information between individuals, and then these individuals realize that these ones are in a better position, and then they start moving towards the correct maximum. So this is the main idea behind the swarm consensus. So you start with many different candidates, and you locally refine these candidates, but you also see information from the other candidates, and at the end they all converge to something. And normally this is always, or most of the times, it is the global minimum. So maybe it is not a very high resolution, especially because to speed up the process and also to reduce the amount of local minima, we work with very low resolution images. But the shape, the overall shape is normally good to start an initial volume, to start an optimization process, standard refinement process. Okay, reality, all these algorithms that we have been talking about, they assume that there is a single structure that is compatible with the images, but reality is heterogeneous. And I would say heterogeneous, the initial volume problem in an heterogeneous setup, it is still an open question. So there has been some suggestions like CryoSpark, but it doesn't mean that it always works in all situations. So this talk that I gave in 2013, I finished it with saying there is hope, because at that moment there was a lot of activity in devising new algorithms for solving the initial volume problem. At present, and present it was already 4 years ago, but at present I would say this is not a bottleneck anymore. The reason is that there are so many algorithms and there are so many ways to combine the output of the different algorithms. Not so many, but so this kind of consensus, there are a couple of them. But there are enough tools to solve this problem in a safe way. So at present, you should be aware that if you use a wrong initial volume, then you might be in trouble, but there are enough tools to overcome this situation. So this is all for this lecture, and see you in next one.